Okay, it doesn't seem like something we should have to test out. Watch. Gravity worked. But wait. Being good scientists, is one trial enough? No. Trial 2 also worked. Trial 3. I'm seeing a pattern, yes? Okay. You've had gravity happening your whole life, but you might not have thought about what it is. And today, we start with what gravity is, what it seems like it is. Before the end of this unit, we talk about relativity, what Einstein came up with, and it'll totally make all of this like kid stuff. But we have to learn this stuff first before we can blow it out of the water. But gravity. If I came to you and I said, Neva, find me the mass of this. There's my scale over there. What would Neva do? Somebody just shouted out. Yeah.
You find its equal weight in grams.
All right. So you'd go over here and she would make it equal on this. Okay. You can. Yay, it's already done. Right? But what if I'd have gone to Neva and said, Neva, find the weight of this? Would she have done the exact same thing?
No.
Think about it. She would have done the exact same thing. Yeah. No. We've been using the words mass and weight interchangeably, like they're the same thing. And when we're in this classroom, we can get away with that. Because mass and weight aren't really going to change all that much. Okay? If your mass is going to be here, your weight's going to be here today, tomorrow, the day after that. If your mass is here, your weight's going to be here today, tomorrow, everywhere else. But when we learn about gravity, we're going to learn that mass and weight, we might have a changing weight, even though the mass stays the same, and they're not always going to be perfect parallels. And so your whole life you've been saying, hey, find the weight of this for me. Hey, find the mass of this for me, and you do the exact same thing, and that's going to be kind of, we're going to have to use those words differently now. Because mass, hopefully you remember this, mass is how much matter an object contains. So how much matter there is inside of an object is how much mass it has. Okay? Now if I go to the moon, will my mass change? Because I'll have the same number of atoms inside of me. Okay? The amount of mass that I have won't change by location. So I can be on the moon, I can be in space, I can be Mars, and I will have the same amount of atoms inside of me. Weight, on the other hand, is different. Weight is the amount of force that gravity is exerting on a mass. So if I step on a scale, that scale is measuring how much force I'm pushing down on it, and that scale is going to give me a weight back. Now here on Earth we can say, okay, well your weight is this, your mass is that. They're pretty well equal. All over the Earth is pretty universal. That stops being true once we start talking about space and the moon and space stations and other planets. Weight can change. Weight can change depending on your location. Which one can't ever change? Which one can change occasionally? Okay, now, suppose for a second that we have triplets. These are some big triplet, identical people, identical in every way. One of them is here on Earth. Okay, on Earth, their mass is 100 kilograms. Their weight on Earth, I'm just going to tell this to you so you don't have to figure it out, is going to be 1,200 newtons. Now a newton is about 1/4 of a pound. Okay? So these are some big people, but 1,200 is not that big. It's like 300 pounds. On the moon, here's someone on the moon. Okay? What's the mass of that twin on the moon? Excuse me, triplet on the moon. It will also be 100 kilograms, correct? But what is their weight going to be? Is it going to be 1,200? No. Is it going to be 0?
No.
Okay, let's call that 700 newtons. The weight is going to be 700 newtons. Okay, are their masses the same? Are their weights different? Okay, here's my question to you. I said these were triplets, right? The third triplet is somewhere in between, out here in space. Okay? You need to figure out what is the mass of that triplet, what is the weight of that triplet going to be. Okay? You can guesstimate, you can do whatever you want with the weight, but it will be an exact thing. So take a minute, try to figure out the mass and weight of this triplet. The mass of the twin should have been the easiest. What's the mass of our triplet? 100. Thank you, 100 kilograms. But what is their weight?
0.
I hear 1, I heard 0. What do you say?
3.
99.50. I'm sorry, I know I let you call out, but I need to hear Emma Ann. The answer, Andy,
14,000.
0 newtons. They're weightless. They are without weight. Weightlessness means no weight. 0 newtons. Okay? Now there is gravity here, but we're going to be talking about how even though there is gravity, this person, if there was a scale right here, oh look, there's a scale. Will that scale feel a force pushing it down? Yeah. Precisely. Going back. Mass. Mass. The units for mass are kilograms and pounds that we most often use. The units for weight are in newtons. So, what is gravity then? So, we're going to keep it simple for this class. And for now, gravity is going to be the attraction between objects that have mass. Anything that has mass has gravity. So, I need 2 things that have mass. Andy and that book. Okay, now, is there a force of gravity between Andy and that book?
Yes. Yeah.
Are they 2 objects that have mass? Yes. Now, is that force of gravity big or small?
Small.
That's a small force of gravity, but it is there. We could calculate it. We could do it pretty easily. It's going to be like a billionth of a newton or something crazy like that. But it's a real thing. Think of your favorite object at home. There is a force of gravity between you and that favorite object. But there's also a force of gravity between everyone else in the world and that same object. Okay? There's a force of gravity between you and the person you're sitting next to. There's a force of gravity between you and the wall, you and the ceiling, you and the floor, you and Mount Everest. Have its own little thing going on. Okay? There's gravity between you and that person you really like. Okay? Any objects that have mass have that gravity. Okay? So, this picture. Thank you. Here's an apple. This apple has a force of gravity between it and the apple tree. Between it and a mountain in Tibet. It and Antarctica. There's a force of gravity between it and the core of the earth. There's a force of gravity between it and a polar bear. Between it and Japan, Fiji on the other side of the earth. All of those forces are on that apple. Now, there might be a force this way and a force that way. What's going to happen to those 2 forces when you add them together? They cancel out. What happens when you add all of these forces together? What way does the apple go when you drop it? It adds up to going straight down towards the earth. The earth is the main thing we have gravity towards. So when you have that much force going, in all those directions, I've got a force going that way and a force going that way, You add those two forces together, you get a larger force going that way. And that's why everything falls towards the center of the earth. What I want you to do here, in your own words, please describe what's happening in this picture. What do all these small arrows mean? What does it result in? So in your own words, here's what's happening as that apple falls towards the earth. Why it falls straight down. Gravity is a force that acts between any two masses. So we've seen that. But now there's one last bit of notes. The two factors that affect gravitational attraction, we've talked about one of them. What's the one we talked about? So it's with the M. Mass. The other one is distance. Make sure you get that in your notes. Mass and distance. So you've already in your notes, you have two dots, two spheres. These two spheres have this arrow. What's the arrow represent? Gravity. So if this arrow gets bigger, what's that represent? Stronger gravity. If the arrows were smaller, what would that represent? Okay, we're going to have some examples with bigger arrows and smaller arrows. And make sure you draw your arrows huge if you want to remember that they're bigger, and tiny weak sauce if they're weaker, okay? So, the force of gravity acts between all objects. What if these objects were bigger? Okay, if we made the spheres twice the volume, gravity might double. So in this case, if mass increases, the force of gravity increases. Or, in my little shorthand, if you increase mass, you increase gravity. I'm going to keep going. You can catch up. On the other hand, what if you made them further apart? If you took these two spheres and moved them out to here, what would happen to those two red arrows? What would happen to the force of gravity? It would be less. As distance increases, on the other hand, the force of gravity decreases. Or, as you increase distance, you decrease gravity. Do you notice how these arrows are nice and large and these arrows are nice and tiny? That shows that there's less gravity there. Make sure that in your notes you get those differences. All right, so we're almost done. The notes sheet. You'll notice that you have a nice big blank page. What I want you to do on that blank page, and think of this as homework if you need to, is I want you to take everything we've covered on that front of that notes page and in your own words, with your own drawings, everything else, copy it onto that blank page. Okay? And yes, so you're taking your notes and you're putting it on the blank page because you might be able to follow me and write everything down, but that action of trying to translate it, okay, I'm going to try to do it with one picture. And that one picture is going to have one Earth, and it's going to have two spheres, one that's close, one that's far away. And one's going to have a large gravity, and one's going to have small gravity, and one's going to be a big sphere, and that's going to have even more gravity. If trying to translate that into your own diagram is a really good practice for, do I understand this? Can I translate it? Or am I just looking at the notes and thinking I'm understanding it? So trying to put it in your own words on that blank sheet of paper is really good practice. The other thing I want you to do is answer this question. Okay? Why do astronauts weigh less on the moon? Should seem simple, but this is the last thing you should do. Why do astronauts weigh less on the moon? As you are translating your notes onto that blank sheet of paper.